Welcome back, guys. In this lecture, we will discuss some questions on predicate logic. Uh, let's start. In previous lecture, we discussed some properties of quantifiers and nested quantifiers also discussed. And now we will discuss some questions based on that. So let's go. All right. So first thing is first question would be a question like is for all x px or for all x qx implies for all x px or qx. Is this a true or false? All right. So let's discuss this. Uh, to solve this, let x has values. Uh, x has values like x1, x2, x3, and dot dot dot. Right. So here one thing to make sure note is that to make this logic invalid here, we have to make whole logic or we can say expression false. All right, by putting values of x uh, at least once. So it should not be a tautology to be invalid. Right. So let's do this thing right here. What we are going to say do is uh, let some color change the pen. Alright, change the pen, then it will be like this. It will go like this of now. P of x1 and P of x2 dot 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 for all x and y. Right? Or this is or q is I think q of x1 and q of x2 dot 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 implies what implies P of x1 or Q of x1 and P of x2 or Q of x2. So, alright. So for to make this logic false, what we are saying to make no not here. Uh, to make this logic false, we can say invalid. We have to somehow make what we say is to false. Let's say this whole expression is m and this also expression is represented by n. So to make this false, or we can say invalid, now we have to make m to true and n to false. Alright. Right. So true to false. True implies false is always false. This is the property to travel of implication operator. Or note one thing more. Note for here is for all px1 or for all x qx imply for all x px or for all y qy equivalent. Alright. So this is the scope of this. This is bounded to qx, and this x is bounded to px. Alright. So let's move further from here. Where we can go from here is uh, let p of x1 is true, p of x2 is also true, right? Then and q of x1 uh, q of x1 and q of x2 and q of x3 is false. Alright. So what we are going is to put these values. P of x1 here is true and true and dot 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 true, right? Or false and false and dot 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 false. Alright, which implies P of x1 was what? True or false, and true or false. Alright, and so what we will get from here is true implies what we will get here from here is true, which is true always. So it's a tautology. So this expression is valid. Alright. So it's to make a expression valid, it should be a tautology. So it's a tautology. It is a valid expression. Alright. Next question we will cover is right. Next question is here is like this question: for all x there is some alpha, implies there exists some x, alpha and beta. Alright. So to solve this, solution would be like that. This is a predicate function, so alpha 1 and alpha 2 and like this implies alpha 1 and beta 1, or alpha 2 and beta 2, and so on, right? To make this logic invalid, so here we are we are trying to prove it invalid. It is easier, right? So alpha 1 is true and alpha 2 is also true. True and true implies this is false, this is also false here. So This is false, or false is always false. So true implies false, the whole is false. So this is not a tautology, not a tautology. This implies invalid expression, right? And next question is like, uh, so this is a very important question here. Let me discuss with you. This is a very good question. Question is like, there exists some x for all y here, for which a of xy and b of xy, right? And not c of xy. Wait a minute, guys. I have some call here. Hello. All right, guys. This was just a little bit. Sorry. Sorry, guys. The disturbance. All right. So next would be like what? How to? So question is, so is equivalent to what? Right. So answer would be like that. Solution. So first make a note for this, that complement of for all x px would be would equivalent to, there exists some x for not px, some x for not px. Okay. This is how it works. And second note would be like that. Note second is complement of x implies y here equal to x complement plus y complement is xy complement. Is like that. So what we are doing is, we are complementing this whole expression. Alright. So this is would be like, uh, for all x there exists some y, right, for which a of xy, right, and b of xy implies c of xy. Alright. So this is how, because it all whole expression complement means a of xy or b of xy, and right. So or C complement the cy. So this is, yeah, this is right. Let's finish it and do it properly. Right? So if we are complementing this whole expression, for which it will give us there for all x there is some y, and ax comma y complement, or bx comma y complement, or cx comma y. Right? What we can do is we can convert this expression with different, right? This or expression with in this form. Can we take it in this form? Uh, if we can, then it would be nice. So how we can do this? Uh, x bar plus y. Let's say this is y only, all right? And this is x. This is x and this is y. We are complementing this. Right? Complement whole thing. So what we can do is here axy and bxy complement or cxy. All right. This brings us to a equation where axy and bxy implies cxy. All right. This is how we do this. For all x, ax and y. So this is how we do it. This is very not very simple, but not very hard also. This was simple logic. And next we will discuss some translation equations. All right, guys. So what is translation? Right, guys. Let me discuss whole of thing. Translation. What is translation here? Uh, so we are trying to translate some statements. You can say propositional statements into logic. All right. So how we can do this is uh, for all. This is a what is this is what quantifier, right? So this is a quantifier. Then this for what's this quantifier can be used? It can be used for all. It can be used for every. It can be used for any. It can be used for all. Existential quantifier can be used for uh, there exists and some and a, you can say a n, right? For example, if x is, let's say x can fly, right? And bx can are saying x is bird, right? And for this, domain is universe, all right? So how we do this statement? All birds can fly. So statement is all birds can fly. Alright. So how do we translate this into logic? So all is coming. So what we are saying this, how we can do this is for all we will use this quantify. Alright. For all x, alright, which is true, all birds and fly. For all x, fx and bx both are true. Alright. So this is how we do this. Alright. So no. This is not how we do this. Here, all birds can fly. If it is a bird, then it can fly. So bird is a sufficient. Bird is sufficient condition for flying. Alright. For all x, bx implies fx. Alright. If it is a bird, then it can fly. This is how we do it. But if domain was birds only, then for all x, f all birds can fly. Right? Like that. Now, next statement would be like next statement. Some birds can fly. Some means there is existence in some birds. So how we do this? There is some eggs which can fly. There is some eggs for which birds and aphids. Alright. This is how we do. Some birds can fly. There exists a bird which can fly. So next statement is there exists a bird which can't fly. There exist some eggs for which px and not fx is true. Right? Which cannot fly. This is the true statement for that. This is the logic. The next question would be like practice is here. We are doing practice only. At least or also existential. At least every any or. So our next example would be we are going to delete this. Alright. So next question is birds can't fly. So one note is default domain is universe if it is not integer. If it is integer, then it is real number. So birds can't fly. So what we are saying is birds is a sufficient condition for not flying. For all x, right? For all x, if it is bird, then it cannot fly. Right? Example is birds can fly. So All birds can fly? Yes, for all x. If it is bird, right? Birds can fly if it is bird or fx. Like it. For all x, bx for all. Birds can fly. It is a bird or for this is all. This is correct statement I think. And now we will do is we will jump for the next question. For this is the next example. Next example is fx x is fast and dx x is dangerous and cx x is a car on expressway. Right? Right. So domain would be domain domain is all cars on expressway. Okay. So statement is every dangerous car on expressway is fast. So every dangerous car on expressway is fast. Car is always fast. So car on expressway X is for dangerous. Car and dangerous is sufficient for fast. Right? So for all X, if it is car and dangerous, then it is sufficient for fast. Is it like this? Dangerous is fast. So every dangerous car is only car on expressway. Alright, this is uh, dangerous only. Dangerous only. I was thought thinking like that only. Next question is alright. Next question is domain is all objects in the storeroom. Why don't you so question is domain. Domain would be all objects in the storeroom. In the storeroom. So what is the statement here? Every bicycle in a storeroom is red. We need to translate this in logic, practical logic. So what we can say, every bicycle, we can every practical quantifier this for every bicycle. Let's say bx represent bicycle for, or let's change color of pen. So not showing anything. Yes, this is clear. For all x, for all x in storeroom is red. Every bicycle in storeroom is red. So if it is bicycle, then it is red. Alright. I think this is the best way possible to represent this in logic. The bicycle, we can say bicycle is sufficient condition for object being red here. Like next question would be, everything in the storeroom is red bicycle. So everything in storeroom is red bicycle. So for all x, if it is red bicycle, red red and bicycle for all x, all objects red and bicycle, ride and bicycle, right? And next would be example. Every tall boy play cricket. You can say every tall boy play cricket. So what we are saying is, every tall boy, if it is a tall boy, then it's play cricket. Right? Tall and boy. Oh wow, is this a thing? All right, tall boys are precious. All right, this is important question. Uh, Question here: pearls and diamonds are precious. So if it is pearls or it is diamond, it is precious. Alright. So this is or here and की जगह or लगेगा, because this is pearls and diamonds are different things, not one thing. Right? This is very important. Similar like this here. Lions and tigers attack when hungry or threatened. Lions or tiger attack hungry or threatened. Tiger attack and threatened. No, this is not hungry. Right. Next property here is I will show that to you. Next property here is uh, let's clear the canvas for you. Right. Next property is note. I think note here. If P implies Q and R, if P implies Q implies R, it is equivalent to P and Q implies R, right? But P implies Q implies R is not equivalent to P implies Q implies R. This does not hold, right? This is very important. Question and note here. For like dx and right. Next translation and statement is if x comma y x has visited website y, right? What we are saying ax domain all students in college. I need to replace it. I think college, right? And y is all website. Forgive. All What happened here? Right. So no need to refresh. Next topic is next translating at least at most and exactly. Right? This is important topic. So we will give some examples here. Domain is all objects on table, right? And function is here. Predicate function is x is an apple, right? So statement would be like this. Statement is no apple on table. You see. So how can we present it like this? No apple on table is x is an apple and all objects on table. So for all x, uh, for all x not in x, we can say not of x ax. Alright. Uh, there is some x which is apple complement. For all x, this is all though both are equivalent to each other, so no problem. And next is next question is uh, at least one apple on table which is greater than equal to one. Alright. How we can do this? At least one apple. There exists some apple. Alright. There is a state which is an apple. Alright. Alright. This is how we do it. Or we can say, or there is some x for all y for which x is equal to y and which is apple implies ay. Ay is true. So what is this? X is equal to y here. How we can do this? Mm, right. Exactly one apple on table. Right. Exactly. We will translate exactly here. So we will take help. There exists some x for which this is apple and for all y for all y x is not equal to y implies not an apple. Alright, this is very important. Uh, and this is true. X is apple, but at the same time, for all y, x where x is not equal to y implies not what apple. Right? So this is very important. and or we can say at most and at least one, right? At most and at least one. At most one and at least one is equal to exactly one, right? So so next, right? So second question would be, statement is at most one apple on table less than equal to one at most. So how can we do this? At most there exists some apple, alright, only one apple. There is some apple, right? There is some apple here. Well, what we are doing here is for all x and for all y, ax and ay, only both are apple only when x is equal to y. Right? This is true, this is also true. If it is true, it is must be true. This is how we do it. Or we can do it like there is some x for all y for which ay implies x is equal to y. Right? For all y, if this is apple, then x is always equal to y. Alright, there is just some x. This is also we can do this. Yeah. Yeah. Yeah, very important questions here. And next would be greater than equal to 2, alright? At least 2 apple on table. So there exists some x, there is some y, for which ax and ay at least 2 apple, and x is not equal to y. This is also one way, but there is another way also. There is another way also. Alright. Another way, or we can do this like there exists some x and there exists some y, for which x is not equal to y and z, for which x is equal to z or y is equal to z implies z is apple. There are many different ways we can do these things. Right? At most two apple with some x, then x is not equal to y, and for all z, and for all x, px is equivalent to. We are discussing some more questions here now, guys. So what we will do is let's not Let's clear the canvas from here. Right. The question is the question is alpha is for all x px equivalent to for all y qxy not qyy, right, implies for all x. So here two interpretations. I1 is interpretation one is domain is set of natural numbers. Then px is x is prime and qxy is y divides x. So for first assumption, what we will do is collect. So what we will do is uh, first assumption is for all x px is equal to by condition y for all q for all y qxy conditional. This is very tricky, I think. Yeah. And this is for all x only. Yeah? Yes. Not qyy. Qyy means what? X divides y. Uh, First do this. Do this what? Qxy is equivalent to for all y. Right? So x and y, this is x here, this is y. So P and Q x, y divide x is equivalent to y divide y, right? Not, not y. If x is prime, if x is prime, right? This is all true, I think. X is prime, man. Let's say x is prime. X is prime, right? So if x is prime, this is equivalent to qxy. So if y divides x, right, prime number, which means y is itself prime, alright, px prime implies what? Implies not y divides y is not y. Why not? Y is self prime number. So this contradiction false. Not qyy is y divides y. Not true. False. false. Ux divided by false, true, y false, not x comma y not x comma y not, for y is equal to 1 and y is equal to x comma y, not greater than 2. So for all y here, y is what we are doing is, I am not getting anything. Rules of inference and right. So in this we are going to discuss some rules of inference and predicate logic. So let's discuss them. Rules of inference and predicate logic. One is let's say px1, px2, whatever px is about for all x. Right. Second would be universal instantiation for all x. Px would be like px1. Right. Third would be existential generalization. If px1, then px1 or px2 or something like that. You can say there exists some xpx, and 4 will be existential instantiation would be x, px, then px1 or px2 or px3, px2 or like that. Right? Next we are going to argument in that predicate logic. Right? We can solve this thing with Venn diagram. So that this is very simple and very tricky also. Let's discuss argument and predicate logic. So first is every x is y. We can every x is y. X is here, y is this, which is growing outside, right? Second would be some x is y. Some x is y. This is x. This is y. Uh, y is getting into x and x is getting into y, right? Third would be like no x is y. This is x. This is y. 4 is not every x is y. You can say some x is not y, which is equivalent to some x is not y. So this is x and this is y. Right? Y x and x is going back and y is going back. And this is negative. All pens are green. Some pens are invalid. We are trying to manage this. Some notes are also there. Uh, if we are trying to give some notes here, let's do this. Right. Some note would be model. What is model? Combination of domain and predicate proposition and predicate or proposition function which makes the truth value formula true, which makes the truth value of formula true. Combination of domain and predicate proposition. What is co-model? Model plus which makes the truth value of formula false. This formula. Size of model. Size of model is size of domain only. For example, for x or x px, then there exists some model of size 1, where a domain 10 x is equal to 10. Why not? What is this domain? Alright guys, thank you very much for watching this video. We will meet you in the next one.